Hi, my name is Rachel. Welcome aboard on this exciting journey through the world of blockchain. Today, we are going to explore the chapter Blockchain Data and State Management. Just like planets orbiting in space, blockchains also have their own data universe. In this lesson, we'll discover how blockchain stores, organizes, and manages information. By the end, you'll understand the hidden machinery that keeps Ethereum and other blockchains running. Haiche, why data matters in blockchain. Every blockchain is a giant shared database, but unlike normal databases, blockchain data must be secure, verifiable, and resistant to tampering. Managing this data is what ensures trust in decentralized systems. State management defines who owns what, and data structures keep everything in order. This chapter will show you how blockchains balance storage, security, and speed. Merkle trees, the basics. Imagine you want to check if a puzzle piece belongs in a huge puzzle without seeing the whole picture. That's what Merkle trees do in blockchain. They are special data trees that link transactions together using cryptographic hashes. Each leaf is a transaction, and the top root acts like a summary of the whole block. If one piece changes, the root changes, making tampering obvious. Inclusion proofs in Merkle trees. Merkle proofs let you prove that a transaction exists in a block without downloading everything. Think of it like showing a train ticket stub instead of carrying the entire train schedule. With just a few hashes, you can verify that your transaction is part of a block. This makes verification faster and keeps storage light. It's why Bitcoin Lite clients can trust the blockchain. Ethereum's Merkle-Patricia Trie. Ethereum takes Merkle trees to another level with the Merkle-Patricia Trie. This data structure stores accounts, balances, and smart contract code. It combines a trie, prefix tree, with a Merkle tree to allow quick lookups and updates. Every account in Ethereum has a place in this tree. When the tree's root changes, it reflects the new global state of Ethereum. Why Patricia Trie matters. With millions of accounts and contracts, Ethereum needs efficient storage. The Patricia Trie helps compress and organize all this data. It ensures that even the tiniest change in state is captured securely. The root hash is stored in every block header, acting as Ethereum's state fingerprint. This allows any node to independently verify Ethereum's world state. Sparse Merkle trees. Sparse Merkle trees are a new design being researched for future Ethereum upgrades. Unlike normal tries, they allocate positions for every possible account, even if empty. This sounds wasteful, but with clever math, it allows fast proofs and smaller storage requirements. Sparse trees help in verifying balances or smart contracts with very little data. They are stepping stones to scalability. Verkle trees, the next step. Ethereum's developers are moving towards Verkle trees. These use a different type of commitment, vector commitments, to make proofs much smaller. Instead of hundreds of kilobytes, proofs can be just a few kilobytes. This is important for stateless clients and light nodes. Verkle trees could be the backbone of Ethereum's future, enabling more participation without heavy storage. Full nodes. A full node downloads and verifies the entire blockchain. It checks every block, transaction, and state change. Full nodes are the guardians of decentralization. They don't rely on anyone else's word. They store the latest state and some history, but may not keep everything forever. Running one requires time, bandwidth, and disk space. Archive nodes. Archive nodes store every single state that has ever existed on Ethereum. They allow you to see what the blockchain looked like at block number 1000,000 or any other time. These nodes are huge in size, often multiple terabytes. While not needed for normal users, they are crucial for explorers, analytics, and history-based applications. Think of them as blockchain museums. Light nodes. Light nodes are the lightweight versions of blockchain clients. Instead of storing everything, they download just block headers and use Merkle proofs for verification. This makes them fast and resource-friendly, perfect for mobile devices. They rely on full nodes for extra details, but still verify independently. Light nodes keep the network more accessible. State growth problem. As more transactions happen, blockchain state keeps growing. Every new account, token, or contract adds data. Over time, this makes running a full node harder. If state growth is not controlled, fewer people will be able to run nodes. This threatens decentralization and pushes blockchains towards centralization. State pruning. One solution is pruning, which means removing old or unnecessary data. Just like cleaning your phone storage, pruning gets rid of states that aren't needed for consensus. Nodes only keep recent data while discarding older snapshots. This keeps storage requirements manageable while still preserving trust. Without pruning, blockchains could bloat beyond usability. Stateless clients. Another idea is stateless clients. These clients don't store state themselves, but instead rely on proofs from others. Whenever they need to check something, they are given a proof, like a Merkle or Verkle proof, to verify. This makes clients lightweight and easy to run. Stateless clients could allow anyone to verify Ethereum with just a laptop or even a smartphone. Storage rent proposals. To fight unlimited state growth, Ethereum has explored storage rent. This means users would pay rent for keeping data on-chain. If rent is not paid, data could be deleted or archived. It forces developers to think carefully before filling the blockchain with contracts. Though controversial, storage rent could help balance sustainability and usage. Events in blockchain. Smart contracts can emit events, signals recorded in transaction logs. These are not part of the blockchain state but are very useful for apps. For example, a token transfer event tells wallets and explorers that a transfer happened. Events make it easy to track what's happening without reading the entire blockchain. But how do we find these events quickly? Bloom filters for event indexing. Ethereum uses Bloom filters to index events. A Bloom filter is a clever math trick that tells you whether an event might be present. It can give false positives, but never false negatives. This makes searching fast without storing exact indexes. Wallets, dApps, and explorers rely on these filters to quickly find relevant logs. Data availability challenges. Even if data exists, is it always available to everyone? That's the challenge of data availability. If block producers withhold data, others can't verify blocks. This problem becomes critical in scaling solutions like rollups. Ensuring data availability means making sure every node has equal access to the information needed for validation. Off-chain, indexing with subgraphs. Indexing with. Sometimes blockchain data is too complex to query directly. Off-chain indexing tools like the Graph solve this. Developers can build subgraphs that organize blockchain data in structured formats. dApps can then query this data using GraphQL, just like asking a database. This makes blockchain apps much faster and more user-friendly. Conclusion and wrap-up. We've journeyed through the universe of blockchain data and state management. From Merkle trees to Verkle trees, from full nodes to light nodes, from pruning to stateless clients, each part plays a role in making blockchains efficient and secure. We also saw how events are tracked, how data availability is ensured, and how off-chain indexing supports apps. Just like galaxies hold stars together, these mechanisms hold the blockchain together. Thank you for joining me on this journey.